Hello, welcome, and an excellent evening. I am fresh back from Revision 2026, which is the world's largest demoscene event, supposedly, according to the website at least. It's a demo party. What is a demo party? What is the demoscene? I think you should know if you follow my channel. The demoscene is where coders, musicians, and all kinds of artists, from pixel artists to whatever, come together and celebrate digital arts, being creative, being friendly to each other, and having a great time. And there are a lot of competitions for PC, Amiga, old school, that is C64, ZX Spectrum and similar, music, graphics, and others. And there are also very specialized competitions. One of those competitions is the 256 byte intro competition. The rules for this competition is usually that the executable, the whole program, must not be larger than 256 bytes. That is like 2 text messages roughly on old dumb phones. It is super limited space, so to speak. The whole code has to fit in there. In memory, it can do whatever it wants, basically. And basically, all of the entries usually are for MS-DOS, as you can see here, because MS-DOS has the advantage that you can use COM files, which are basically just dumps of machine code, which don't have any header, so you get 256 true payload bytes. And yeah, you can maximize your space, basically, that you're using for code. Also, MS-DOS has a rich interface of BIOS and DOS routines via interrupts, so you can initialize graphics modes quite easily with a couple of bytes. And some of the video modes, such as the VGA 256 color mode, mode 13 hex, is very simple. It is just a plain frame buffer, and you can just pump bytes into it. So that maps very well to these very constrained programs, so to speak. And this year, the first place, I mean, there were, please check out the whole competition. It's up on YouTube. You can watch it, rewatch it. There were some very nice things. Tunnel Overlord is a small animation with a running man and a robot shooting lasers. Amazing stuff. Endbot is the evil bot, the mascot of this year's revision, exploding on screen. Also very amazing, with noise and 3D scrolling. Reflector is some weird abstract triangles, very nice to look at. Abyssos is some rotation and zooming through 3D cube space, also very amazing. Disintegration was lovely to look at, kind of like 2 abstract planes shifting on top of each other. It looks fantastic, and I have to check how that was done as well. But the cake, so to speak, was taken by this production, Rainbow Surf, by Plex of BionFX. And the important thing here is it does not look like that much, but it is only 16 bytes long. The 256 byte competition means you can't go over 256 bytes, but you can sure go under. And I think this is the smallest intro that I've ever seen that does something really useful. So you can see here it's 16 bytes. Let's run it here on DOSBox X. It also runs in vanilla DOSBox and on real PCs. I chose DOSBox X because I can reboot it easily. And yeah, warning for flashing lights. Sorry, I will put that in the video description. If you're photosensitive, you probably shouldn't watch that. But you can see these look like waves of colorful characters that move to the left, more or less. Yeah, looks quite nice. And you can't stop it or anything. So I have to send Control-Alt-Delete to reboot the whole machine. There we go. Yeah. But how does this work, you ask? We can actually have a look by using Turbo Debugger, and we will also have a look later in the source code. Yeah, the whole program is actually the first 16 bytes of what you can see here. There's some leftover of other stuff, but the program ends actually here at this address 10E. That is the 16th byte because it goes from 0 to E. COM files always load at offset 100 in an arbitrary code segment. The code segment currently is 4B5F, but that is totally random. And Turbo Debugger actually sets up the registers not as MS-DOS would, especially the source index register. And let's have a look at the DOS.com startup register table that you can find on the web. And almost any MS-DOS version, except for some weird stuff, IBM DOS, very early versions, they will set SI all to 0, 100. So that's what we need to do, because right in the first instruction, SI is used as a pointer. So we press Ctrl-C to change the value, and we type in 100 hex. So that is actually what we need here. And yeah, this is actually very useful for size coding, because you can assume if you run it under any of these DOS variants, and DOSBox behaves like an MS-DOS variant, that AX and BX will be null, CX will be FF, DX will be the code segment, SI will be 100, DI will be FFFE, and the stack pointer will also be FFFE. The base pointer will be something arbitrary. Yeah, but there will be a 09 in the upper byte, so to speak. So that's something that you can use if you need any of those values and don't want to load them into memory yourself. Okay, let's go through this step by step. First thing, ES and AX will be filled. This means load ES from the pointer that SI points to. And SI currently points to 100, so it will actually load C404 into AX, which is interesting. And it will load the next word, AB48, into ES. Fascinating. Let's do that. We can see that AX is now 404C4, which is the opcode here, 04C4. And ES is AB48. And this is interesting because AB48 lies in the middle of VGA graphics memory. But if you go to a segment calculator, let's put that in here, AB48, and what was it, 04C4, that's AB4944, or AB94 and offset 0004, that's smack middle in VGA memory. The text mode, however, is starting at B800. So let's assume we want to reach the last bit that we can from this, which is AB48 and FFFF. We do see that we now have something in BB47. So that's smack middle in the text area. So we're passing B800 segment, and eventually we can write into text memory even. You are out of luck if there is some other cards in between or some other RAM or after that, but these addresses are actually taken so that they overlap only the VGA memory, and that's an amazing trick. This saves the crucial bytes to make this fit in 16 bytes. So that's pretty crazy. The first instruction that does something useful is this one here. It decrements AX, and we can try to do an increment or even a knob and see what happens, because I figured out that this decrement AX is actually necessary. Without it doesn't work. And then we will store whatever is in AX into ESDI. ES is AB48 and DI is currently 00 and will be incremented. There you go. Now DI is 2 because we wrote one word. We now wrote something into VGA graphics memory which we can't see yet. The next thing will add something on top of AX, namely ESDI-52. In this example, I think the original is this hexadecimal. Let's check the source code. Yes, this is hexadecimal. It's actually 82 decimal. That is what was in the original code. This basically takes a character that is, if you think of the text screen, which is 8 characters wide, you would assume that it takes the character that's one up and one to the left, or maybe two to the left. But each character on screen is made up of 2 bytes, because you have the character and the attributes, like the color. So it takes something that is 40 characters downstream, like if you're in the middle, it will go here, and then even 1 character further. So it goes halfway across the screen with a wraparound. If you're on the left, it will jump to the previous row. And the only explanation I have for that is that this makes it look good. I played around with a couple of different numbers and you can achieve very weird results. So I suggest you try at home different variants of this. And the next thing, we did that now. AX is now BE3. We add another value, namely the one we not just wrote, but the one after that we just wrote. Basically taking the value from the previous frame. Okay, that's what's happening here. Now we are at BE2. Aha, we first had BE3. So for some reason there was a -1 in that space. And I stepped through a lot of this and it seems like most of the memory gets filled with -1, which is probably FFFF at some point. And I think the way this is built up will lead to that fact. Anyway, to get some kind of attenuation, and the waves are basically a kind of attenuation. We start with a high value and then we need to make it from frame to frame, we need to make it become smaller. We shift the value that we now added by 2 to the right, which is a division by 4. So BE2 becomes 2F8. And then we're done. We do the jump back to the beginning and we'll decrement the value in AX, which is now 2F7. It was 2F8. And the loop begins from anew. Now we overwrite the pixel we just read and do the same adding and shifting. We're getting to something slightly smaller, 285. And if we continue this, we will get ever smaller numbers. You can see here, now we are at 25E, and I can run it a couple of times. There's another 25E that we're writing, but eventually it will get even to smaller values. But that's the whole thing. There's nothing that lets you stop this. And we are still here in VGA graphics memory, so no way that we could see this. We can run this, and it seems to work fine. It needs a little bit to converge, so to speak. And I'm gonna send Control Break to get back to the debugger. And right now we are still in AB48. And which destination index? 6194. That could be, let's calculate if we're already in text memory. Let's check that. A before 8. 6194. That's B161. Okay, that's not yet in color text memory. That would be in monochrome text memory, but we are not monochrome. All right. So let's switch to the editor and let's see what happens if we take the deck.ax and replace that with a knob, for example. What if we didn't need that? We could, of course, leave out the knob completely. We still get 16 bytes. We will try and reload this. This will eventually crash, so we might be unlucky while restarting this because this writes into memory like crazy. But we'll try it. Okay, this works somewhat, but not as we expected. It seems that the decrement is needed to fill the memory from top to bottom with everything. I think there's probably outside of the screen we still have funky waves going on. This also looks more repeating, more regular. But this didn't help. So decrementing doesn't work. What about incrementing? Does that change anything? Let's assemble again. Then open. And rerun. Now, this leads to a black screen. This goes in the completely wrong direction. Doesn't seem to work at all. So it seems that the deck.ax is actually needed. I can't truly explain why that is the case. So if you have any idea, that would be interesting, because all it does is take away a little bit. So my assumption is that if we get to a 0 here while doing the right shift, this will actually give us the FFFF and lets everything start from scratch again. That's my assumption. It will do the wraparound and then a new wave can appear on the screen. If we don't do that, then there's no wraparound. Yeah, and we are basically out of luck. I think that's what is the issue here. This is basically reseeding everything with something fresh. And for everything else, decrementing by 1 will not do much to the visuals, so to speak. Then another question is, why 82? I would have assumed that minus 162 would make sense, because then you would truly go 1 up and to the left. So let's see what that looks like, if that makes any difference. Again, reloading. And now we have A2 as our constant here. And yes, it converges differently, but seems to work as well. But now we have more like a horizontal motion, at least in DOSBox X. I think in DOSBox proper, normal, it looked slightly different and there was a little bit of an upward movement as well. There are some blobs propagating. So I think this also is doable. You can do that. It's a nice effect. Other stuff to try. What about -1? What do we get then? Open. Okay, this is pure noise. Let's abort that. That's pure noise. What about -255? What does that result in? Because those are like the corner cases. Very similar, but slightly different noise with a little bit of 2 lines at the top that look special. Okay, let's take something like -127. That's 7 bits set, basically. Let's try that. And run. Also very noisy. So those actually produce a lot of noise. Let's try some weird number, like 23, some prime number. Maybe that is something worth watching. My assumption would be that everything outside of these corner cases might be converging to something very similar. Actually, no. It's also very noisy. So it seems that 82 and 162 are kind of special cases. What about 202? That would be 40 characters down again. Would that make any difference? So maybe it has to do with the size of the screen. Maybe. Interesting. It does converge to something. Again, more of a horizontal movement. Yeah, but it looks more useful than before. Let's try out 22. Or 42 we had? Yeah, let's try 22. That's again a little bit down from what we had. Okay. There was more upward movement and the blobs are getting smaller. Yeah, I think that you need to have some kind of fraction of the screen size. And I think the person that wrote this chose the 42 because it looked good. I think that is the reasoning. And I think, yeah, this is again the 42. This gives us the blobby looking waves. This is probably the neatest effect, one could argue. Okay, let's break here. Then I thought, this is writing left and right into memory everywhere, very dirty. And could we make it nicer by investing more bytes? So what I thought was, let's initialize the segment register correctly. So, but as minimally as I can. AX is 0, I know that, so I move into AH, the high byte, B8, so I have B800, and load that into ES. I think that's probably the shortest that I can do. This will load the VGA text memory into the ES register correctly. Then we still do the deck AX because you know we need the wraparound. We do the store string word. This time we do the -82, but we can play around with other stuff. We also do the shift right. And then we compare with 8000. We could also do 4000. I think I did that for testing. I think this doesn't change much. This will write exactly one VGA screen page. And if we didn't reach it yet, then we jump back to L. And if we reach that, then we clear DI and start over at the top of the screen and jump back. So this will give us, let's see, I need to reassemble this. This is called simple. And that's 26 bytes. So we lost 10 bytes. We're still below 32 bytes. What would this look? Sorry, what would this look like? And would it look any good actually? So this is our new program. It's a little bit longer. It goes up to here. This is actually what we saw earlier in the memory because DOSBox doesn't clear that. And if we do that, we get a hang, I think, because I need to reset the virtual machine, reboot guest system, or maybe I should just send, let's send a Control-Alt-Delete. Where is it? Where is it? Where is it? Send special key, send Control-Alt-Delete. That's booting. Let's try this. Okay, this is much more flickery. So this doesn't look nearly as good as the original, even though it should be more correct. And I think the reason for that is that we don't write outside of VGA memory, actually. I think that is an issue. If I were to, for example, write something like B7 and then extend our iteration to 2 screen sizes, I think it might actually look better, because then there's something on top of the screen that can be interpolated by this addition and shift right. So if we try to do that, yes, it's a bit too quick. The iteration is much too fast because now we're not iterating over a whole segment, but only over 8,000 bytes, so to speak. And that also makes it look less good. So you would need to slow it down. Hence, I think even if you were to make it a bit more safe, it doesn't look better. And I think this is actually the most minimal and most elegant solution that you can have. It's a bit annoying that it starts in the middle of VGA memory, but it doesn't matter because it stays in VGA memory and it should work on all machines that have a VGA card. On other machines, it will do probably weird things. And it might run on an EGA card, maybe, because that should have very similar memory map in text mode at least, so that is fine. And it could perhaps even run on a CGA card based machine because there the text memory is also at B800. Yeah, but that is my analysis of Rainbow Surf. What is it called, right? Rainbow Surf by Plex of BionFX. And I think it totally deserved to win this year's 256 byte competition. And it is a very interesting 16 byte intro, and I don't think you can do a smaller thing that still does something interesting to look at. So yeah, tell me your thoughts about this program in the comment section. Tell me if you ever did some size coding, on which platform, for example, and how that was. I did one video about the game of life in 256 bytes with some sound as well, and I will link to that in the video description. You can have a look at that too. It was very interesting to figure that one out as well. I wonder if you could make that even smaller into 128 bytes or something, probably without sound, but I think that will be very difficult to squeeze down even further. But people have done amazing things. That's it for today. As usual, you can follow me on Mastodon over at chaos.social/root42. And yeah, you can support me as well via the usual means. Just look in the video description. But until then, see you in the next video. Bye!